So next, I have a quick quiz about the conditional probability and the Bayesian theorem, and you can take a look at it. I'll read through this problem, and then you can think about it for about 5-10 minutes, and we should have a solution after that. So, for example, Adam visited his doctor to get tested for contagious disease. I'm not saying it's COVID, but you can consider it, could be COVID, which is found in 10% of the population. The test run by the doctor has 75% accuracy to detect the disease if it reads positive. So that's a condition. Now, Adam received a positive result. What is the possibility that he has the disease? Okay, that's the first question. Second question is, after he got the result, he visited another doctor independently and also got a positive result for the same test. What is the possibility now? Okay, you might think he goes to another doctor, and now shouldn't that possibility be the same? So that's a good question to ask, and you can think about it a bit more and try out this analysis following the formulation I gave previously on the previous slides about Bayes' theorem and also the conditional probability calculation. So this is a diagram showing you how the Bayes' theorem works. If you click it, point you to this Bayesian interface inference, and you can click the first one, Bayes' theorem, and it tells more or less like what we are doing, we are trying to do for the exercise. You can click you can change the values, and then you can carry out the analysis. You can test one patient, or you can test the remaining. So what it does is sampling the population and try to carry out all this test for you. Okay, I'll not go into details for this one, but you can look into that after you figure out why the results is like this. But we'll get back to our problem, and I'll show you why the result is looking that way. So this comes a solution to the quiz. So first we have multiple symbols to explain here. P plus here means the chance to test positive, no matter carrying disease or not. And then PD bar plus means the chance to carrying the disease when test positive. And the P plus bar D here means the chance for testing positive when carrying the disease. And the PD here is a chance for carrying the disease or not. So PD is simply the 10% that for general population, because we know this contagious disease is carried by 10% of people. So that's a chance for carrying disease. That's 10%. That's the only one with a clear label here. We know for sure it's working that way. Now, we also know that there is a 75% chance for you to be really carrying disease if you test positive. So that is when you carry disease, when you carry really disease and you test positive, that's a P plus bar D. That's a chance of testing positive when carrying disease. That's a 0.75. Now, based on the Bayes' theorem, the PD bar plus, which is what's the chance for you to be detected for you to carry disease when you test positive, it is simply the P plus bar D, like the one I'm showing in the Dr. 1 case, times PD divided by P plus. So P plus bar D here is simply 0.75 times 0.1 divided by P plus. But we don't know what the P plus is, so we can simply estimate this P plus with the P plus bar D plus P plus bar, and then negative P plus negative D and negative D, P negative D, which is the when you are test positive if you are not carrying disease, which is a 0.25, and the possibility that you are not carrying disease, which is a 0.9, which is a 1 minus 0.1. So that's how you calculate the P plus at the denominator. So with all the numbers plugged in, you can get 25%. That's the chance for you to carry the disease while test positive. For a random person with no prior information about the disease, the test has only 25% chance to be accurate, mainly because the big majority of the population, like 90%, doesn't carry disease. And also the testing facility or whatever you use for testing, it's only 75% accurate. So a big chunk of population actually is hidden because they are not tested or they just don't carry disease. So with that big denominator, the possibility for you to carry disease when tested positive actually is not higher than, much lower than 75%. So for a random person with no prior information about disease, the test has only 25% chance to be accurate. Consider you have no information, you didn't do any test. You only know that everyone, it's possible to carry disease with only 10% of a chance. That's 10% for a general population. Then no matter how many doctors you're going, you're still getting same results because you know that you only have 10%. But now after you finish testing from the first doctor, and now your chance is not 10% anymore. You're 25%. The main reason is you already have some prior knowledge than a random person. So you need to update your PD. Instead of using 10%, you should use 25%. Because you already know what's going on there and you have a better knowledge. And you did the test and the test give you some information about your current status because you already tested positive. Then you plug in the number, then after you test with the second doctor, your chance for carrying the disease when tested positive for the second time jumped to 50%. So after prior information changes, the test now has a 50% chance to be accurate. So that's the non-trivial part for this kind of quizzes. And I think it's helpful for you to understand how probability theory works and how Bayesian theory works. And you can try out similar examples yourself and try to see if you can understand what's going on there. Again, it's a non-trivial example. It requires some understanding about statistics and prior knowledge and about Bayes' theorem to get this kind of results. So with that, I'll conclude this module.